Assalamualaikum warahmatullahi wabarakatuh. Okay, today I want to explain more on topic 1. Okay, fluid mechanics for topic 1. Okay, properties of fluid. Okay, so learning outcome at the end of this chapter, students should be able to define the basic properties of fluid mechanics, understand and analyze fluid flow problem, and list out and apply fluid basic equation. Okay, concept of fluid mechanics, so we can apply that fluid engineering application on breathings, water jet, swimming, pumps, fans, turbines, airplanes, and etc. Okay, so if in your final or in your test asks you to explain the application of fluid mechanics, so you can explain about this point. Okay, breathing, water jet, swimming, pumps, fans, turbine, airplanes, and etc. Okay, so now we look at the concept of fluid mechanics. Okay, for this is the figure 1 and the figure 2 here. Okay, figure 1 illustrates a solid block resting on a rigid plane and stressed by its own weight. Okay, its own weight here. Okay, the solid sets into a static deflection. So when the static deflection shows as a highly exaggerated dashed line. So they have the dash line here to resisting shear without flow. Okay, so now we look at the figure 2 here. The liquid and the gas at rest in figure 2 is require the supporting walls to eliminate the shear stress here. Okay, so this is the liquid and this is the gas. Okay, so they have the two types of fluid. Okay, the liquid and also the gas. Okay, so now the liquid retains its volume and forms a free surface in the container. Okay, and if the walls are removed, shear develops in the liquid and a big splash result. Okay, and if the container is tilted, shear again develops wave form and the free surface seeks a horizontal configuration, pouring out over the lip if necessary. Okay, so this is the concept of fluid mechanics based on figure 1 and also the figure 2. Okay, so this is the definition of fluid mechanics. Okay, mechanics is the oldest physical science that deals with both stationary and moving bodies under the influence of force. So the branch of mechanics that deals with bodies at rest is called statics, while the branch that deals with bodies in motion is called dynamic. Okay, so this is the definition of the mechanic. So now we look at the fluid mechanics is defined as the science that deals with the behavior of fluid at rest, okay, when the fluid is in statics, or in motion when the fluid's dynamics. So and the interaction of fluids with solids or other fluids at the boundary. So this is the definition of fluid mechanics. Okay, when if in your final or in your test asks you to explain what the fluid mechanics, so you can explain what the mechanics and also the fluid mechanics here. So this is the theory. Okay, so the theory for the fluid mechanics. Okay, so now we look at the units. Okay, the units for fluid mechanics. So they have the quantities here and also the unit here. Okay, so the quantities of mass, so the unit is kg. Okay, the quantity is distance, so the unit is meter. Time for unit second, and the force using the Newton, and temperature is using the degrees Celsius or Kelvin. Okay, so this is the based on quantities and also the units. Okay, so we use the SI unit because we not using the US unit, so we use the international system SI unit. So SI unit is written in small caps. So example, especially in kilogram, so we use the symbol of kg, meter based on m, and also the second is the s. Okay, if the unit is named after someone, the unit starts with a capital letter as a watt, W. Okay, Pascal is the P, and Newton is using unit the N. Okay, then this is the unit here. So an exception is for the unit of liter. Okay, so the liter is using the L, okay, the biggest L. Okay, for the density, okay, so we using the symbol of this one. Okay, this is called the density. So the density of a fluid is the ratio of mass to volume. Okay, density is equal to mass divided by the V is the volume. Okay, the density of fluid change with temperature and pressure. Okay, so based on unit of density is kg per meter cube. Okay. So, and for simplicity, the density of water is assumed to be 1000 kg per meter cube. Okay. So, this is based on the table 1, density of water as standard sea level atmospheric pressure. Okay, from temperature from the 0 to 100 with the density of water here. Okay, so this is the table of the density of water. So the density of liquids and solid depends more strongly on temperature than it does on pressure. Okay, at 1 atmosphere, for example, the density of water changed from 998.2 kg per meter cube at 20 degrees Celsius to 977.8 kg per meter cube at 70 degrees Celsius. So from this one, we know that the force for the density for water with the different temperature, so they have also the different density. Okay. So now we look at example 1.1. Okay, calculate the gasoline's density at 20 degrees of Celsius. So the mass and volume are 60 kg and 0.5 meter cube respectively. Okay, so the solution for this calculation is, we know that the equation of density is equal to mass divided by the volume. Okay, based on unit kg per meter cube. So density is equal to 60 divided by 0.5 of the volume. So we get the 120 kg per meter cube. So this is the example for calculate the gasoline density. Okay, now we look at example 1.2. Okay, given specific gravity of mercury is 13.55 at 20 degrees Celsius. So the calculate mercury's density is using the same equations. Okay, the density is equal to mass. Okay, the density is equal to mass divided by the volume here. Okay, so the density, so this is give you the specific gravity. Okay, so this is specific gravity here, so the pre-mercury here. So we get the to get the mercury here is from specific gravity times by the 1000 here. Okay, so actually this is for the mass for volume. Okay, so we just look at the using the volume of, we know that using the specific gravity equation. Okay, at the next slide, I will explain more on the next slide. So we know that the specific gravity is also density divided by the density of water. Okay. Okay, this is the density of fluid. Okay, the fluid is using the mercury, so you use this equation here. Okay, so that's why we use this equation. Okay, St is specific gravity is 13.55. So the density of mercury, to get the density of mercury, so divide by the 1000 kg per meter cube. We know that the density of water. Okay, so the density of water, we use this side here. Okay, so now we look at the example 1.3 here. Okay, so using to find the density, okay, using the weight. Okay, so this is using the weight of the liquid with the 15 kilonewton, and the volume is 3 meter cube. Okay, so we know that the mass of liquid using the m is equal to weight divided by the gravity acceleration. Okay, so you just put all the value here. Okay, the weight is this one, 50 kilonewton. We know that 15 times by 10 power of 3. okay, divided by the G gravity acceleration is 9.81. So we get the mass of liquid here. Okay, so we know that the density is equal to mass divided by the volume here. Okay, so mass, we know that the mass is in kg. So just put the value here and divide by the volume. So we get the density here. Okay, so this is the part of calculation in topic 1. Okay, so that's the step by step. Okay, so now we look at the specific gravity of relative density. Okay, actually this is part of the slide that I have explained the previous slide. Okay, how to get the specific gravity. Okay, so now we look at the slide on specific gravity here. Okay, is the density of a substance is given relative to the density of a well-known substance. So this is a Sg is equal to density of fluid, okay, divided by the density of water, okay, at 4 degrees Celsius. Okay, so we know that the density of water, we use the 1000 kg per meter cube, okay, as the calculation in the previous slide. Okay, so the relative density of a gas is the ratio of the gas density to the density of hydrogen or air at certain pressure and temperature. Okay, relative density is dimensionless. Okay, so they have no unit. Okay, so they have no unit because the relative density or specific gravity Sg is dimensionless, so no units because the density of fluid divided by density of water, so they have no units on that equation. Okay, so example 1.4, so calculate the specific gravity or relative density for A engine oil. Okay, with density of oil is 880 kg per meter cube. Okay, seawater, okay, with 1025 kg per meter cube, and the mercury, density of mercury is 13570 kg per meter cube. So the solution here to calculate a Sg of oil, so they give you the density of oil, so you must divide by the density of water, so you get the Sg of oil is 0.88. Okay, just use the density of oil divide by the density of water is 1000, so you get the 0.88. Okay, now at the B, using the seawater here, so use the density of seawater 1025 divide by 1000 here, so you get 1.025. Okay, so you get the specific gravity or relative density for seawater. Now we look at the mercury. Sg mercury is using the density of mercury divided by 1000, so you get the 13.57. Okay, so this shows that mercury, okay, the mercury and also the seawater here are denser than water. Okay, so there's more denser than the water here. Okay, so because it was 1.025 and 13.57. Okay, seawater and the mercury here. Okay, so now we look at the specific weight, the properties that are the properties of water or fluid. Okay, the specific weight is the weight per unit volume of fluid at certain temperature and pressure. Okay, using the specific weight is equal to density times by the G, and the unit is Newton per meter cube. Okay, where G is the gravity acceleration and unit of specific weight is Newton per meter cube. Okay, so this is the specific weight. Okay, specific weight of water is 9.81. Okay, kilonewton per meter cube at 4 degrees Celsius. Okay, so specific weight of water, so we use the 9.81. Okay, if in temperature of 4 degrees Celsius. Okay, so now we look at the specific volume here. Okay, with the symbol of V, small v here. So we know that the specific volume is the volume divided by the mass. So we all is equal to 1 divided by the density. So the unit of specific volume is meter cube per kg. Okay, this is the specific volume. Okay, now we look at the calculation for find the specific weight, density, find the specific weight, density, okay, relative density, because the specific weight is this one. So you just find the specific weight, density, and relative density of a liquid with volume 6.5 meter cube and weight 55 kilonewton. Okay, so we know that the specific weight is equal to density times by the g, or m over v times by the g, okay. So just or w divided by volume. Okay, actually you must remember that this specific weight, from this basic equation of specific weight, so we can get the density, mass divided by volume, because this is the density, okay, times by the g. Okay, so w, okay, mg is equal to w. Okay, m mass times by the g, we get the w and the volume here. So we get this equation for specific weight. Okay, just use the weight here, 55 kilonewton, times by 10 power of 3 divided by the volume here, 6.5. So we get the specific weight. Okay, and just find the density. Okay, just put all the value here using this equation. Okay, density. Okay, after you get the was here, you just divide by the g here, so you get the value here, okay, of the density. So now look at the specific volume. So the specific volume is equal to 1 over density. Okay, 1 divided by the density. So you just put the value here, so you get the specific volume here. Okay, so the relative density, okay. Okay, sorry, actually this is for specific weight. Okay, so this is specific volume, not specific weight. Okay, just correct the okay, so this is specific volume. Okay, so you get this one. Okay, and this value here. Okay, so the relative density, just put the this one, so we get the 0.8625. Okay, the relative density for this example, 1.5. Okay, so now we look at the compressibility. Okay, refers to the change in volume V of a substance that is subjected to a change in pressure. Okay, so with the different volume, okay, so they have the different temperature, compressibility. So because the volume here, okay, so the usual quantity used to measure this phenomenon is the bulk modulus of elasticity, or simply bulk modulus using the E here, compressibility. Okay, so you just because this is more on theory, so you must know what is the compressibility. Okay, actually compressibility, it refers to the change in volume of a substance that is subjected to a change in pressure on it. Okay, so this is for the compressibility. So now we look at the dynamic viscosity. Okay, dynamic viscosity is the measure of the resistance of fluid against shear stress or tensile stress, or simply viscosity is measure of fluid friction. Okay, according to Newton's law of viscosity, so shear stress is equal to, shear stress is equal to F is the force divided by the area. Okay, so F is shearing force. Okay, and the area, okay, the shearing force of this part here. Okay, so we get the area dy. Okay, the shear strength is the theta is equal to dx dy. So we get the rate of shear strain. Okay, d theta over dt is equal to dx dy times by 1 over dt is equal to du dy here. Okay, so actually this is dynamic viscosity. Okay, now they've known that the Newtonian fluid and also the non-Newtonian fluid. Okay, actually the Newtonian fluid is the shear stress is linearly proportional to the rate of shear strain. satisfy that Newton law of viscosity, and the line passes through a origin. Okay, this is the Newtonian fluid. Okay, so as example is water, air, kerosene, and mercury. So this is more on an example of Newtonian fluid. Okay, so the non-Newtonian fluid is using this blue line here. Okay, so and also here. Okay, so when the straight line red here is the Newtonian fluid, example as the water, air, kerosene, and mercury. Okay, non-Newtonian fluid is the paint, polymer, solvent, mud flow, blood, and etc. Okay, so this is the difference between Newtonian fluid and also non-Newtonian fluid. Okay, so if in your final or in your test asks you to differentiate between the Newtonian fluid and also non-Newtonian fluid, so you can explain about these two difference of fluid. Okay, so and also you can sketch this graph. Okay, the between the differentiate between non-Newtonian and Newtonian fluid. Okay, so fluids for which the rate of deformation is proportional to the shear stress are called Newtonian fluid. Okay, example as water, air, gasoline, and oil. Okay, blood and liquid plastic is non-Newtonian fluid. Okay, in one-dimensional shear flow of Newtonian fluid, shear stress can be expressed by the linear relationship. Okay, as that I explained in the previous slide. Okay, so use the equation of the shear stress is equal to viscosity times by du over dy. So this is the shear stress. Okay, shear stress is proportional to the rate of shear strain. So we get this equation of shear strain. So viscosity times by du over dy. So where u is the dynamic viscosity. So unit of dynamic viscosity is Newton per second per meter cube. Sorry, per meter squared. Okay, Newton second. Okay, Newton second per meter squared. So the unit of dynamic viscosity. Okay, so this is the table of dynamic viscosity based on the different fluid here. Okay, the different fluid with glycerin with the different temperature. So they have the dynamic viscosity here. Okay, when the engine oil with the different fluid of SAE. So we get the dynamic viscosity here, and the mercury, ethyl alcohol, and water here with the different temperature. So the dynamic viscosity also different. Okay, and so on. Okay, so now we look at example 1.6 here. A thin plate located 0.1 mm away from a rigid boundary requires 1.2 Newton per meter square force. Okay, the speed of 2.5. So between the rigid boundary here, to find the dynamic viscosity of the fluid contained between the plate and the rigid boundary. Okay, so given that distance between plate and rigid boundaries dy, okay, between the plate and rigid boundaries is dy is 0.1 mm. Okay, 0.1 mm, so we can convert to meter here, 0.1 times by 10 power of negative 3 meter. Okay, though we know that the plate velocity u is 2.5 because the speed here. Okay, the speed is 2.5 meter per second. So the change in plate velocity du is equal to u minus by 0. Okay, because the change on plate here. Okay, so u minus by 0. So we know that get 2.5 here. Okay, and force on plate is 1.2 here, Newton per meter squared, and shear stress using the equation here. This one, dynamic viscosity times by du dy. Okay, so we get that the shear force here, force on plate is 1.2. Okay, to find the dynamic viscosity u here, and du over dy, we know that du is 2.5 and the dy is this one, 0.1 times by 10 power of negative 3 meter. So we get the dynamic viscosity is 4.8 times by 10 power of negative 5 Newton second per meter squared. Okay, so that's the calculations. Okay, so now we look at the kinematic viscosity. Okay, kinematic viscosity is the ratio of dynamic viscosity to density. Okay, so this is the equation of kinematic viscosity. So two common unit of kinematic viscosity are meter second per meter meter squared per second, and one stock is equal to 1 centimeter squared per second, or 0.0001 meter squared per second. So typically the water of kinematic viscosity is this one. Okay, don't worry about this one because all the value of kinematic viscosity if in your test or in your final will given in your text in question. Okay, so dynamic viscosity in general does not depend on pressure, but kinematic viscosity does. Okay, so this is depend, okay, between the dynamic viscosity and kinematic viscosity. Okay, so now look at the example here. Okay, a rod of diameter 20 mm and length 150 mm move at a speed of 25 meter per second here. Okay, fill with the oil. So to find the dynamic viscosity and also the kinematic viscosity. Okay, so we get here. Just look at the rod here. Okay, fill up here, and we know that the given data is in this tag here. So we know that the F is 12 Newton, diameter of rod is 20 mm, length of the rod is 150 mm. Okay, speed 25 meter per second, and dynamic cylinder here. Sorry, diameter cylinder is 50 mm. Okay, so now the solution here are impacted by the shear force A. Area is pi dl. Okay, so this is the area of the rod here to find. So just put the value here. Okay, and times we get the diameter times by the L here, length rod here. So we get the here. Okay, so you get the area. Okay, now shear stress, using the shear stress is equal to force times by area. Okay, sorry, force divided by the area. So you get the value here, 1273.24. And also the shear stress using this equation. So you just put all the value here and you get the dynamic viscosity of 0.7639 meter second per meter squared. Okay, and you get the kinematic viscosity. Just put the dynamic viscosity divided by the density. So you get the value here. Okay, so this is the step by step how to find the dynamic viscosity and kinematic viscosity. So now we look at example 1.8. Okay, the velocity distribution of flow over plate is given. Okay, so this is actually the using calculate the velocity and the shear stress, okay, on the boundary. So put all the given data, okay, in your text here. Okay, they give you the velocity distribution. Okay, so U and shear stress at y is equal to 0 meter and y at 0.25 above the plate. Okay, given 0.85 Newton second per meter squared, and U is the distribution here. Okay, so from the U here, so you must find du over dy. So use based on mathematics. Okay, du dy. Okay, so you get the from the U here, you get du dy. Okay, and get the shear stress using this equation. So just put the value here until you get the shear stress. Okay, and at y is equal to 0. So du dy, you just put the y is 0. So you just get the 5. Okay, 5 second here. Okay, so you just put the in shear stress with y 0, so you get 4.25. Okay, when at y 0.25, so just put the y at 0.25, so you get 1 second here. So you just get the shear stress with y 0.25 meters, so you get the shear stress is 0.85 Newton per meter squared. Okay, so this is concept to find the velocity and shear stress on this boundary. Okay, using the velocity distribution is given. Okay, from U, you change to du dy. After you change, so you can get the shear stress. Okay, now we look at the thermodynamic properties. Okay, thermodynamic properties are important when temperature affects fluid properties. Ideal gas law. So we use the P, okay, times by the volume is equal to N RT. So this is thermodynamic properties. Okay, where P is the absolute pressure in kilopascal, V is volume on gas in liter, T is the absolute temperature in Kelvin, M is mole of gas. Sorry, not M, N here. Okay, just N here. Okay, just put the correct the N here. Okay, so the N here. Just put the N. Okay, mole of the gas. R is the gas constant with use this equate. Okay, so what pressure will be exerted by 20.16 gas hydrogen. Okay, so use the equation that is given here. Just put all the value here. Okay, in this equation, ideal gas law here. So just put and you get the pressure in kilopascal. So this is this is based on the pressure, okay, using the previous equation of ideal gas law here. Okay, so you just put all the value here. Okay, T with the temperature, with the liter volume, okay, and the pressure. So you get the value here. Okay, so this is for the example 1.9. So now we look at example 1.10. So the absolute pressure is also carbon monoxide in a ship. Okay, we will compute the density, specific weight, and specific volume of the gas. So the given as the P is pressure is 500 kilopascal. Okay, temperature is 27 degrees Celsius. So you calculate convert to Kelvin. So you must plus, okay, 27 degrees for Celsius. You must plus 273.15 to get in unit Kelvin. Okay, you convert the degrees of Celsius, convert to Kelvin, you must plus with 273.15. Okay, so atomic weight of carbon monoxide. Okay, we know that actually this value is given in the table. Okay, I forget to put the table here. I just put the weight of atomic weight. Okay, the atomic weight of this one. Put here for the carbon monoxide. Okay, weight of the carbon monoxide is this one. Okay, actually this refer to the table here. So, but in your test or in your final, I will give this value. Okay, no need to worry. Okay, actually this is based on the table that I get from the reference book. Okay, so now if in your test or in your final, I will give this value. Okay, no need to calculate. Okay, so you just know how to use this equation of ideal gas law. Okay, so after you get this one, so you just put to get the density. Okay, using the ideal gas law, so we get the density. So after you get the density, you must find the specific weight. Okay, if we get the density, so we can get the specific weight. Okay, just times by the gravity here, 9.81. So we get the 1.966 Newton per meter cube per mole here, because this is based on per mole here. Okay, because it's also the gram per mole. Okay, the specific volume, so just put the value here, so we get the. So now we look at the surface tension. Okay, the surface tension. Okay, how the surface tension is applied. Okay, actually is a drop of blood forms a hump on a horizontal glass. Okay, a drop of mercury forms a near perfect sphere and can be rolled just like a steel ball over a smooth surface. And water droplets from rain or dew hang from branches or leaf of trees. So this is the application of surface tension. Okay, is a property of the surface of fluid that allows to resist external force due to cohesive forces between molecules, and unit of surface tension is force per unit length or energy per unit area. Okay, actually this is the concept of the water drop here, and the insect, okay, the length of the insect for the water here. Okay, and also the pin based on the water also. So the example of surface tension actually from the leg of this insect and the water here, so they have the surface tension. Okay, the surface tension between this droplet, okay, water droplet with the leaf here, so they have the surface tension here. And also, okay, actually it's the surface tension here, that the color yellow that okay, this is the surface tension. Okay, so now we look at the free surface. Okay, this is the cohesive force between molecules below the surface are shared with all neighboring atoms. So those on the surface have no neighboring atoms above and exhibit stronger attractive force upon the nearest neighbors on the surface. This enhancement of the intermolecular attractive forces at the surface is called surface tension. So this is the surface tension from the molecule A, molecule B, and molecule C, and the D here. Okay, from the water here, okay, until to the free surface here. So they have the surface tension here. Okay, so this the A, the molecule of A is they have the all surface tension is around of the A here, and also the B here, and the C just around at the water here. So they have surface tension here, and the D and the surface tension as here. Okay, and so this is the concept of surface tension based on these atoms A, B, C, and D. Okay, so now we look at water droplet. Okay, water droplet here. Okay, force, and they have the forces here and the surface tension here. Okay, and what force acting on the droplet. So the water droplet is all force is acting on this droplet here. Okay, so this is total of pressure force here is using this one. Okay, so actually the total of tension force is this one. Okay, actually this is based on pressure force on surface tension. Okay, so in equilibrium, so we know that the pressure forces, okay, pressure times by pi over 4 d squared. So actually this is area, okay, is equal to surface tension times by pi and times by the d here. So the pressure force is equal to surface tension. Okay, so with the different fluid, so they also have a different surface tension here. Okay, this is the table. Okay, and we get the P pressure force is equal to 4 times by surface tension divided by the diameter d. Okay, so we look at the example here. Okay, diameter water tank is filled with air through a pipe to produce bubbles. Okay, compute air pressure required by the pipe to form bubbles with a diameter 10 mm at temperature. Assume atmospheric pressure is 0. Okay, so the based on the atmospheric pressure is 0. So the given data is d diameter 10 mm. So convert to meter, 0.01 meter. Okay, surface tension of water at 30 degrees Celsius is this one. Okay, actually based on this table. Okay, actually between this table. Okay, they give you the 0, 20, 100, and 300. So the 30 degrees Celsius, they based on this one. So you must convert to this temperature. But don't worry, in your test or in your final, I will give the table with different temperature from 0, 10, 20, 30, and so on. Okay, so no need to convert that. No need to calculate to find this one. Okay, I will give you the table. Okay, so the surface tension of water, this one, is given 0.0712. And use the equation of the pressure here is equal to 4 times by surface tension divided by diameter. So just put all the values so you get the pressure of required by the pipe to form bubbles. So the pressure for surface tension. So we get the value. So the capillary action occurs when one end of capillary tube is immersed in the liquid. All forces holding a liquid together are called cohesive forces. So the forces of attraction between a liquid, okay, and another surface are adhesive force. So this is more capillary based on water, and this is the mercury. Okay, so this is water and this is the mercury. They have the difference capillary action. So the water, if in the water, so the capillary of this road, so they have increased here. Okay, but for the mercury, they just based on the this one. Okay, water rises in the capillary tube because the adhesive forces between the water and the glass are quite strong. Okay, sufficiently strong to draw the liquid up against the force of gravity. But for the liquid in mercury, the cohesive force are greater than the adhesive force. Okay, so the level of the liquid inside the tube is actually depressed. Okay, so the level of the liquid inside this tube is actually depressed. That's why we get this for mercury, but for H2O water we get the rises in the capillary tube. Okay, so the concept of this water and also this is mercury. Okay, so they have the meniscus and the liquid surface. So this is called meniscus. Okay, meniscus on the liquid surface is U shape. So based on the U shape, because the forces between the water, okay, because the water and the glass here are stronger than between water molecules. Okay, that's why we get the U shape. But for the mercury here, so we get the meniscus on the surface of mercury is convex or dome. Okay, or dome shape. Okay, based on mercury is dome shape because the attractive forces between mercury atoms are stronger than the attraction between mercury and the glass. Okay, so this is the concept of surface tension force and the capillary tube. So we use this equation. Okay, so this equation H is equal to 4 times by surface tension times by cos theta and this one. Okay. Okay, example 1.12. Compute the minimum diameter of glass tube of capillary rise in the tube does not exceed 0.25 mm. Okay, assume the surface tension of the water is 0.075. So you just, the given data here, just use the equation of capillary rise. H is equal to 4 times by surface tension times by cos theta divided by specific weight times by the diameter. So cos theta is 0. Okay, the cos theta is 0 is equal to 1. Okay, cos theta is 0, cos 0 degrees is equal to 1. So that's 4 times by the surface tension here is 0.075, but the cos theta is 1. Okay, actually the cos theta is 1. Okay, the cos theta is cos 0 degrees is equal to 1. Okay, so we get the value of this one is, just put all the value here. Okay, just put all the value so you get the H is 0, D, you get the D is 0.1223 meter. Okay, for the diameter. Okay, the minimum diameter of glass tube. So now we look at example 1.13 here. Also the same calculation to get the, this is to get the H, okay, rise of water. The previous slide to get the diameter, but using the same equation. Okay, just put the this value. Okay, so compressibility and bulk modulus using the E here. Bulk modulus E is defined as the ratio of change in pressure to the rate of change of volume due to change in pressure. Okay, so where dP is the change in pressure causing a change in volume. Okay, when the original volume was V, so the unit is the same as the pressure Newton per meter squared. So the negative sign indicates reduction in volume due to increasing pressure. Okay, at normal temperature and pressure, so E water, bulk modulus of water is 2.07 times by 10 power of 6 kilonewton per meter squared. So bulk modulus of air is 101.3 kilonewton per meter squared. Okay, so this is the concept of the bulk modulus, okay, of compressibility in water. I over E is, okay, compressibility of water is so small that it is usually neglected. Okay, so this is the problem. Okay, so I will give you that for next. That's all. Thank you. Assalamualaikum warahmatullahi wabarakatuh. Thank you.